In this video, we will learn how to interpret a topographic map for the purposes of determining vertical displacement in an area, as well as determining the gradient of the map in said area. In the previous lesson, we learned how to interpret topographic maps for general understanding. This video will take that understanding one step further to help describe topographic maps. The first item that will be covered is determining vertical displacement. Before we can do this, we have to understand what vertical displacement means. Vertical displacement is the shifting of land in a vertical direction resulting in permanent change in elevation. Note that throughout this course we have been concerned with horizontal measurements such as how far apart locations are or in which direction a front is moving, which can be easily seen by looking at a map. However, a map is a two-dimensional representation of an area, which means that vertical displacement cannot be physically seen. Using the contour lines, though, we can get an idea of what the displacement of an area is. Continuing with our discussion, we now know that vertical displacement refers to the vertical, up and down movement of the surface of the Earth. Let's focus our attention on the area in blue. When dealing with vertical displacement, you need an area you are trying to determine the vertical displacement for. This is typically done along a path, and for our purposes, let's use the transect from Y to Z as shown on the zoomed map. The first step in determining vertical displacement is to determine the contour interval of the map. Going back to lesson 9, we can determine the contour interval by taking two index contours and dividing the number of contours between the two. In this case, we have an index contour of 12,000 feet and 13,000 feet with 5 lines between the two. Taking the difference between the two, we come up with 1,000 feet. And dividing by 5, we find the interval to be 200 feet. Now that we know our contour interval, to determine the vertical displacement, we need to find out how many contour lines did we touch to get from one point to the next. So starting from point Y, we will progress towards Z and count the number of contour lines we touch. We cross 1, 2, 3, 4, 5. Now that we have the number of contour lines, we have to multiply this by the contour interval to determine the vertical displacement. So, multiplying 5 by 200 feet, we come up with 1,000 feet, which is the total distance one would go up in elevation if they were to travel from point Y to Z. Let's do another example. What would be the vertical displacement from point O to point P? We do not need to determine the contour interval again since we have already calculated it. So what we need to do is determine the number of contour lines between the 2 points. There are a total of 9 contour lines between the 2 points. And by multiplying this by the contour interval, we find that the vertical displacement from point O to point P to be 1,800 feet. Now that we know how to determine vertical displacement, let's go back to the larger map and see what the vertical displacement looks like for the entire map. Looking at the transect across the map represented by line AB, we can begin to visualize how this landscape would look if one were to stand where the green box was and surveyed the landscape. We will not calculate the vertical displacement throughout the map, but what we can do is graph it out. And what we wind up with is a graph that looks like the one on your screen. What you see here is that as one goes from point A to point B, there is a change in elevation from around 5,000 feet all the way up to near 15,000 feet. While there are some spots on this graph where the vertical elevation does not change much over a distance, it does give us a good feel for what happens over this landscape. One thing to note, though, is that this graph will change based on where you draw it. If one were to graph this area out with a transect going over the hill in the middle of the map shown by the red box, you would see a rise in the graph, a drop, and then a rise again, as shown on the graph by the red line. This line is not accurate to the landscape elevation and is an approximation of the shape, but it does show roughly how a high elevation between 2 points would be represented. Either way we look at it, this gives us a good feel for how the landscape is shaped. Now let's take this concept a step further, since we have got a good grasp of vertical displacement and what a landscape would look like if one were to look at it from a long distance. We will continue to use line AB for this next process, as we have the graph of the area to help visualize the landscape. We can now calculate what the gradient of the map is. Gradient is defined as the increase or decrease in magnitude of a property, and in the case of this map, it is elevation. Gradient is determined by taking the elevation change over a distance and then dividing it by the total distance traveled to come up with a ratio. What this helps to do is determine how steep an area is based on the magnitude of the number, or how gentle the slope is by how small the number is. In the case of our map, we will have a change in elevation represented by feet, a distance represented by miles, and a ratio stating how many feet are gained or lost for every mile traveled on the map. The first thing to do is to determine the elevation at the start and end of the line, AB, to determine the elevation change over that line. The line starts at approximately 5,000 feet and ends at roughly 14,000 feet. Subtracting these two numbers, we know we have an elevation change of 9,000 feet. Then, taking our scale bar, we can use it to approximate our total mileage covered. Measuring out the 1 mile off the scale bar, we can tick off the miles from one end to the next, and then use the scale bar to the left of the 0 to get the refined measurement of the remainder. Now, counting the number of miles, we get a total of 6 miles, with the small segment at the end being equal to roughly 1/4 of a mile. And adding them up gives us a distance of 6.25 miles, which goes into our equation. Dividing these two numbers together, we come up with a gradient for line AB of 1,440 feet for every mile traveled. While this may not seem like a large change, imagine this number being larger, which would indicate a much steeper slope. To put this into perspective, the gradient from the Everest Base Camp to the peak of Mount Everest is 2,735 feet for every mile gained. In summary, in this video we have learned how to determine the vertical displacement of a region of the map by using the contour interval and counting the number of contours between each point. We have also learned how to determine the gradient of a map to help in assessing the slope and steepness of a region. Please feel free to share your comments and questions with your instructor regarding the content of this video, as well as to receive further guidance on the concepts covered.